sediment supply to the South Atlantic margins. Thank you, Paul.
Thanks very much, Alistair. A lot of what Alistair was showing there in terms of lake systems and sediment supply depends a lot on the sort of accommodation space we have. It also depends on the hinterland evolution. What I want to do here is to show you some work that we've been doing in a case study for part of West African margin, looking at hinterland evolution. Like I said, it's from a case study we did, so there's quite a lot of technical elements to it. Now, in terms of the nature of the problem, there's been a lot of work on the distribution of sediments offshore, and recently Duncan's excellent paper on sedimentation along the margin based on well and seismic data. But one question that keeps coming up is where exactly does that sediment come from? So if we look at somewhere like Gabon, very, very well understood in terms of the late Cretaceous plays, looking at the turbidite plays, as you see here, with the Batanga turbidites and the Aguila. A lot of wells have been drilled, but a question still remains as to where does that sediment really come from, and how can we use that information to extend the play? So here there's been a lot of work about the role of structures to actually direct the turbidites, certainly go quite a way offshore into deeper water. We've got a pretty good idea of the structural distribution in this area, but are all of those sediments sourced directly, in this case from the Agui River, or do they come from somewhere else? So that's sort of the work that we've been starting to look at, and this became even more important, as Alistair's already mentioned, with the subsalt discoveries. This is actually from the recent discovery of Marathon and cobalt, again, here in southern Gabon, in the subsalt. Now this is condensate. I think how much oil is in there, I'm not sure on that one. I haven't seen the latest results. But one of the questions there is how does that fit into the overall story of lake systems and the sediment feeding into the initial rifts in this area? Now, obviously, we can drill this. We can look at a lot of the seismic, get a very good picture. But that sort of thing costs a lot of money. And also, the distribution of that information is quite sparse at this stage. So again, it comes back to using other techniques, looking at hinterland evolution, looking at paleogeography, paleoclimate, to try and get a handle on what the distribution of those plays might be, especially as we look down into the subsalt. Now, the left-hand side here, these are just taken from the literature from various publications, looking in terms of the stratigraphy of the interior basin of Gabon at the top, and then a section from the interior across into deep water in the bottom left. But what we've been doing is building up these sort of paleogeographies, taking that information to try and understand a little bit more about where the discoveries fit in and how the distribution of the different plays relate. Now, this paleogeography is for the Birimian. You can see the lake systems here mapped in. But the questions that I mentioned already is where does the sediment come from? Is it entering through transfer zones within the rifts? Which margin does it come from? This is actually a map of sort of a broad area of the Dentali. And what is the actual size and longevity of these lake systems? Again, we've already heard how important they are. So if we're looking in the south here, these are sort of very narrow, deep lake systems, compared with the north here off of northern Gabon, where we start to see much broader lake systems. And so we're doing a lot of work trying to reconstruct those. Now here, I'm just going to concentrate on the sediment source. And the objectives really are to reconstruct the onshore transport pathways, otherwise known as rivers. It's nice complicated terminology for something very simple. Look at the reconstruction of the hinterland relief, and I've shown that on numerous occasions. That's the paleogeography and the paleoelevation, and I'm not going to really dwell on that. But it's crucial because that forms the boundary conditions for looking at the vegetation and the climate that then impacts on sediment flux. I'll show a couple of figures right at the end of some of the climate results. Using all of that information to then reconstruct the sediment flux, composition, and also the texture of material coming down those rivers. Now, a lot of that is based on empirical work from the present day. Some of the work I'll show here is actually based on Niels Hovis's work out of Cambridge, but there's been a lot of work recently by Savitsky and others out in Colorado. Again, real problem with that is it's based on the present day, which is not always a good basis for doing anything in the geological record, despite what you might have heard. And then finally, looking at transport pathways in the offshore area. So as the sediment's coming down those rivers, it's deposited in delta systems and then out into the shelf. What happens to that sediment? Again, you can start to use modeling for that in conjunction with looking at the overall structure and the bathymetry of an area. And again, we've been sort of looking at some tide and ocean current models for that. But I say what I'm going to do here is actually look at this first part. And it's very much a worked example to show you how drainage analysis and reconstructing the hinterland works. And it's going to take you back, or many of you, back to sort of Geography 101, at least probably. Now, one of the problems here, and going back to this Gabon example, up here with the Agui deltas in the late Cretaceous, is where exactly does that sediment come from? And there's a whole series of different hypotheses as to where it may have been sourced. Now, this diagram here, focused on the Cuvette Centrale area, on the Congo River, highlights those different hypotheses. And you can see they're all radically different. So if you look at Driscoll and Karner's view, was that the Congo in the Cretaceous headed out here into the Agui Delta, and that's why you have this large delta system developed there in the late Cretaceous. It's where you get your turbidite systems. And it's draining this huge area of real estate up here in the northern part of the Cuvette Centrale. Other hypotheses here push it north into Tethys. Again, radically different. Across the Central Africa shear zone, up into Libya through Lake Chad. Ziegler and others put it out here into the Lemurian Bayment. More recently, Stankovic and De Witt put it through the Rukwa Basin, down and out through the Refugee River. And then, back in 2005, Goody putting it out all the way south into the Limpopo. Now, big area of real estate, big diversity of ideas. And of course, a big impact on where all of that sediment's going. It's going to have a huge impact on those depositional systems. So the question is, given what we know, given the sort of techniques that are available, can we get any closer to deciphering which of those might be true, if any of them, and then give ourselves hypotheses which we can test with the well and seismic data that's available? Now, in terms of techniques, there are a number out there. Now, in terms of the present day, and this is sort of what I'll talk about a little bit here, we have a number of data sets in terms of looking at modern-day drainage, which we can analyze through what's called drainage network analysis and landscape analysis. And essentially, it's geomorphology, going back to the 1960s and 70s. And the conclusions of that, we can sort of stretch back into the geological time. At the other side of the scale, we've got conceptual models, and also paleogeographies and observational data from wells, where we can start to sort of link in and say, well, actually, this is giving us an idea of what might be the case, move that forward in time, and the idea is to use all of these techniques to try and reconstruct the history of drainage systems and hinterland evolution through time. Now, the big question is, how far back can you really take the present day, and how can you then reconcile all of these different data sets, and of course, then comparing it with provenance data and offshore information where you have it. Now, sort of conceptual models we're all familiar with. This is actually from Gawthorpe and Leader back in 2000. Reconstructing sort of fasces maps and block diagrams such as this, looking at the rift geometries and how river systems behave. In this case, with axial drainages, short-headed rivers along alluvial fans coming off the margins. And then on the back side of these uplifted rift shoulders, drainages flowing away into the hinterland, perhaps actually coming back around along transfer zones. And those transfer zones become very important, certainly in Africa, because a lot of them have a very long history as shear zones and other crustal boundaries. Now, we can sort of transfer that onto the paleogeographies, and I've sort of already shown you this one already, and start to build up a sort of a model of conceptually what would the drainage be and what would the source areas be. The other side of this is then to look at the present day and work back. So one example here, West Africa, an analysis of all the rivers of West Africa, and in fact also looking at East Africa as well, to try and understand what might be the history of drainage through time. And you can use the present day in a number of ways. One, just simply as analogues and then apply it, as you saw there with that block diagram. The other is to look for changes in the disjuncts in the drainage system that indicate possible changes. And this goes back to geomorphology. Now, the basis of that really is sort of summarised here by Michael Summerfield out of Edinburgh, in that drainage systems have a heritage rather than an origin. And the idea is if you look at a landscape, it doesn't just simply happen. It's a consequence of everything that's gone before. So somewhere buried in that landscape is its history. Those of you who've sort of grown up with Time Team over the last 20 years, there's a sort of landscape archaeologist who goes around, looks at a landscape and says, oh, look at that, that's Roman there, there's a road that's been there for 2,000 years. Slightly different scale, but we're going to apply the same sort of idea. Somewhere in that landscape is buried that history. So how do we do that? Well, one is to look at the network and landscape analysis methods derived back in the 1940s to 60s. And I'll go through some of those. Now, they took the landscape and assumed it followed geometric rules. They just assumed that all things being equal, a landscape will reach some sort of what was called equilibrium, and you could actually apply laws to that. They would follow geometric patterns. So if you look at the dendritic system, very simple. You start off with lots of sources, all heading to one confluence, and there's a geometric rule that applies to that. And they started analysing every river they could find and landscape, and they could see how these things linked together. And the argument was, where there were discrepancies, that was because something else had changed. Now, we can think of this actually in a much more simpler way, in that drainage is a function, or landscapes are a function of slope and the underlying geology. So if you just simply have a block that's tilted, the rivers would just simply run straight downhill, ultimately form into a dendritic system. That's very easy. But if there's geology there, it'll manipulate the patterns, and I'll show you some of those in a second. So what we're going to do is sort of go through, there's a whole series of data sets that go into this, from the digital elevation models to start with, the paleogeographies, and bizarrely at the bottom here, paleobiogeography. This includes, for Africa, fish DNA, one of those things that every geologist should know. And then calculations where we actually look at the networks themselves and the derivatives, long profiles, again, you're going to sort of remember from your geography, and then start to analyse that information. So again, the easiest thing is just to work through a worked example, which is West Africa, so you can see exactly how this fits together. A couple of drainage patterns to start with, just to sort of get people's eye in. This is from the southern part of the Cavesse Centrale. All the rivers are parallel. Being geomorphologists, they kept it very simple. This is parallel drainage. The idea being, you've tilted the landscape due to mantle uplift to the south. All the rivers have been redirected. It's a relatively homogeneous bedrock here. What do the rivers do? They just run downhill. Now, if you're analysing this, the first thing you say is, well, when did that happen? Well, we've got mantle models that say that was sort of Miocene to Pliocene. It puts a date on that drainage system. And in terms of analysis, you could go in and say, right, if that's all Miocene to a Pliocene, I can't apply that sort of pattern, or what I see here in the southern Cavesse Centrale, to a Cretaceous reconstruction. I've got to take that out. I've got to look at it and say, well, actually, what was there before? Now, this has also been examined by Stanley Schum and others with their very large sand tanks. And again, lots of fun in the Midwest of the US, tilting large tanks of sand and water to come up with essentially the same sort of thing. We can look at other areas, and again, radial drainage, very, very simple. This is a basaltic extrusion here in Vietnam. It's basically entrupted the underlying drainage systems. We end up with this radial drainage arrive. Now, we can put a date on those volcanics. We can then take out all of that radial drainage and say, right, what are we left with? What was happening prior to that? And then we've got other things that tell us about changes in drainage systems. This is a very nice example. This is actually the Nyong River from West Africa. If you look, it's been a little bit cut off here. You'll see a typical sort of bifurcation point here. Two tributaries join to form a single river out into the Atlantic over here. Unfortunately, it doesn't quite work that way. And if you look at the river today, it actually bends back on itself into the Congo River. Question, is that how it's always been, or is there any evidence of this river system having changed? And in fact, if we go back prior to this happening, the drainage divide for this area, and therefore the provenance or the sediment source area for deposition downstream, moved from this point here to a drainage divide out here. Again, this is why it starts to be important in terms of exploration. Now, any clues in this that say it's changed? If you look at the tributaries here, you'll see they're all pointing downstream in this top tributary. But in this bottom one, you'll notice that they start off pointing down what was sort of to the left and then bend round. You can see that on just about all of these. Some of them it doesn't happen, but the majority it does. And these are called barbed confluences, which are sort of indicators of a reversal of flow. And so what this is indicating is that originally the flow did go this way, but at some point in the past, the flow has been reversed due to capture over here, and the whole drainage has been changed. So it's this sort of really basic geomorphology that we can use to sort of reconstruct what the river systems were doing, if we can put a date to it. So here's a very simple cartoon showing that in action. At some point I'll animate it, but I know that to sort of worry some of my colleagues when I do that. Again, it's going to depend on the bedrock as to in terms of what it can actually erode. But if we start seeing this sort of evidence, we can again use it as a clue to piece together the hinterland evolution. And then other examples, this actually is not from Africa, this is from Asia, it's just one of the better examples, is we see very sharp changes. This is the Yangtze River to the north, and if I show you on this schematic here, you're seeing these very, very tight changes in the river direction, and then to the south of them, you're getting what are called wind gaps, which are sort of valleys that no longer have water in. And these are sort of used as indicators of capture, that the river here has been captured by the Yangtze to the north, but originally it flowed down along these previous wind gaps. So again, you're looking at a lot of different pieces of evidence to find examples of change. And then for the landscape as a whole, we can sort of represent it, these as in 2D. This is the elevation to the left, total basin area along the bottom here of this graph. These are both normalized. And if you look at a landscape in general, it'll approximate this sort of concave up curve, very, very typical of a sort of typical long profile, of which is also a type of hypsometry, a hypsometric curve, which is what this is. And what Strehler did back in the 60s was say, well, actually, if we look at any landscape, we can sort of place it in this diagram, and we can see an evolution. And we can see an evolution from an uplifted area here down to some stable point here. And of course, that sort of idea relates us to base level and the whole idea of sequence stratigraphy, net deposition, net erosion. Now, the other thing that this diagram does, if we look at paleogeographies and analyze it in this way, that area in 3D is a volume, which is the amount of material removed. And we can test that against the offshore record for our drainage systems. And to get your eye in again, here are two examples of hypsometries. This is the Tana River in East Africa with this typical concave up profile. This is the Nyong River, which I talked about earlier, with a very, very major nick point here, and the whole river system's been uplifted, and this is related to that Miocene uplift. And then long profiles, here are just a form of hypsometry. This is for the Orange River, and again, you see that concave up pattern, but notice that in this particular case, all of these different subbasins seem to have a slightly different history or slightly different shape, indicating possible changes in the river system. And so we can go through the whole of the West Africa and the South Atlantic, both margins, looking for these changes and linking it in with changes in tectonics and changes in sediment source. And I'm going to miss out this one here and come back to that. So working down, let's have a look at this example. This is this is Cameroon here, Douala Basin offshore. This is the Senegal River in the larger part of this figure. In the Wari River, it's just a small little remnant here. Question, is that how it's always been going back into the early tertiary and the Cretaceous in terms of sediment supply to the Douala Basin? Dark blue here represent present-day trends of the modern river systems. The light blue are possible paleo directions, possible paleo trends of the river system. And the red here are the big shear zones that operate through this region. And the sort of things we're looking for here is to say, right, is there evidence of capture here? Now, the actual asymmetry of this is immediately sort of indicative of some sort of change. And it's typical of an area that's been tilted. And again, we've got the Cameroon Highlands to the north. We know this area has been tilted, with the rivers wanting to run downhill, which is in this direction. So that's immediately giving us a clue. Now, the question then is, was this originally comprised a series of narrow river systems parallel to the shear zones? Is that really what we're looking at? We say 2 or 3 outfall points here in the Douala Basin. Again, is there any clue to that? Well, if we look at where this river is stepping down, for instance here at point 4, or over here at 3, they all tie in with nick points. Again, evidence of capture. Cut a long story short, what seems to happen here, the whole of this part of the Gabon area is tilting to the south, erosion is happening to the north, and the rivers here are starting to capture their counterparts in the north of them. So essentially, we've got a story here of capture and changes in the evolution of this margin. How does that affect exploration? Well, it means that what was preceding this, if we know a date for it, were very different sources for sediment outfall into this area and a different volume of sediment going in. Do we know the timing? Yes, we do. Almost certainly a Oligocene in terms of the uplift. So we can start to look at that and say, okay, that's when it started to change. Therefore, if I draw my paleogeography, it's going to look different prior to that. What happens going south? Here we are in the Nyong River, I've already mentioned. Here's that capture point in here. Again, evidence of quite narrow river systems flowing out into the Atlantic, changes due to capture, as you saw here, going into the Cuvette Centrale. And look at this long profile. Again, very, very strong nick point. Pre-existing concave up landscape up here, and then drops away. Now, if we look at a high-pass filter, this is simply showing relief in very colourful map here. Dark blue is areas of incision or erosion, and the reds are the remnants. What we start to see is incision eating its way back as this whole area tilts. So again, you can see this very, very high incision rate here, which is where that Nyong River has been captured. We see the escarpments working their way back north as this system tilts. And we see the same thing as we work south. The Tem River does the same thing. Again, the hinterland has been captured by the Agui River in this case. The drainage divide has moved from here to here. The provenance has changed. To the south, same thing. Narrow rivers following pre-existing shear zones, and again, now being captured due to this tilting in the Oligocene. Same picture with the relief, very high incision rates along these northern boundaries of these drainages as the rivers erode back. And notice this is the Natem shear zone dictating where those river systems go. To such an extent, we can actually see it on magnetics, which keeps Derek Fairhead back in the office happy. But again, it's a major indication of what's driving these river systems and how they're now being changed. And then we go back to the Agui, the story of where does that system come from into the Agui Delta in the late Cretaceous. And the idea of Gary Kano and others that it was coming through here, through this, which is the Ivindu catchment, out into the Agui, feeding back into the Congo. Any evidence of that? Well, this would suppose that the Agui is a relatively mature river system. If it's a mature river system, it should have a long profile that's a very nice concave up profile, which it doesn't. This is the long profile for the Agui River system, and it's a mess. That's a technical term in geomorphology. And what you're looking at here is a whole series of smaller watersheds that have been captured by the Agui, almost certainly during the Oligocene to present day, and subsumed into one river system. So what was happening prior to this, if we're looking at the early Tertiary or the late Cretaceous, is a very different system. And we can then use that to reconstruct where that drainage basin was, where the pre-existing long drainage divide was, in order to then feed into the paleogeographies. Now, to summarize that here, this diagram here shows the long profile of all those rivers I've talked about so far, so the Nyong, Natem, and the Ivindu is this bit here. And you can see, again, this whole idea of tilting, and as we come south, those pre-existing landscapes are all slightly lower. The whole of this system is tilted to the south, and as it does so, erosion acts to the north, captures those rivers. Got carried away there. So again, same diagram in terms of relief. Here we have high incision in the dark blues. Here we see again this erosion along the northern boundary of these drainage basins as it captures, as this tilting leads to capture of the systems. And then we can relate that to the geology in terms of understanding what the actual provenance is. So we're sort of building up a picture here using geomorphology to try and define what those river systems were. In this case, taking it back prior to the Oligocene and then trying to take it further back to the next previous tectonic event. And then once we start to look at the underlying bedrock, reconstructing those paleo drainage basins, we can then start to make a stab at actually what is the sediment flux, what is the character of that sediment, and when does it next change. Now I miss out these next couple here. And that sort of brings on to the last bit, which is once you've got all of that and you've got the paleogeographies, and I've talked about those numerous times, and I know Rob Crosley in the audience here has seen it far too many times, as he told me before I started at lunchtime. What you can then do is put the paleoclimate on, and we sort of mentioned, Alistair sort of hinted at this earlier, thinking about things like carbonate distribution, lake systems and volumes, is we can then link those drainage reconstructions, come up with the hypotheses, draw the paleogeographies, and then put our climate on top. This is actually precipitation, to actually say, well, actually, if we put that water into those rivers, we've redefined them, where's that sediment going? And this is where you can start to make predictions about the character of the sediment and the volume of it. But it all starts off with that very simple geomorphological analysis right at the beginning, taking you back to geography many years ago, I'm sure. But there's some very simple things that we can do. And then working it further back, in some areas, the drainage network analysis continues working into the Cretaceous. Other areas, it falls apart, and you have to then go to conceptual models. But once you get to that, as I said, you can start to put other data sets on top to look at the overall distribution and how that affects your distribution of deposition. Where do you get your carbonates? Where do you get your evaporites? What's the overall amount of sediment coming in? And for comparison here, that first one was Berriasian. This is now in the Campanian. The Gabon block here is uplifted in a very similar way to it has in the Oligocene. Question, is that going to give us a similar story of river capture that we see in the more recent times? But also what it does do is it reactivates the hinterland with these rivers here, and the drainage divide is something out the back here based on that analysis, leads to greater erosion and sediment flux. Now again, whether or not you believe those numbers, this is where you start to look at the work that, say, Duncan's been doing, where you actually look at the observation and the mass balance with sediments offshore. So in terms of what we've been doing here, reconstructing transport pathways, you have to integrate these different things, geomorphology, looking at the paleoclimate and paleogeography, which I haven't really gone into details of. There is an importance of the pre-existing fabric. You saw in the Natem River there with the Natem shear zones. Shear zones are major conduits for rivers, rather like alacasians and rifts, and we can see that all the way down the South Atlantic margin. They dictate where those rivers are going to go. Whoops. And then in terms of actually that particular case study, the pre-Oligocene, I think, is quite clear. The drainage divide is much further to the east. We have a series of much narrower river systems. The Aguri itself is not as big as we see today. It's actually a series of smaller river systems that are putting sediment out along that margin. The other side of that is that there's a climate change as we go through this from dry to wetter conditions in the Lake Cretaceous, which are going to push more sediment down and also greater erosion. Question, though, is was that also the story for the Santonian? And that's a real big question. Do we actually see the same thing happening at that point? And with that, I'll end. This is actually, I have to acknowledge here, it's not all me doing the work. We have a group of about 20, 25 people now working. This is just one of the workrooms. And that is actually one of the key elements in doing any of these paleogeographic maps, as I've discovered, which is large quantities of chocolate. I'm sure there's more hidden away there. Anyway, thanks.
Oh, thank you very much. Thanks, Paul. Spot on in timing. Thank you very much. Well, we have some time for questions for Paul from the audience. If any of you got anything to... Perhaps I can ask one, Paul. You talked about the GUI a lot, but the Lower Congo was always one of the reasons why I think Carner and Driscoll looked at the switch, because it looked like when the GUI switched off, the Lower Congo switched on the Oligocene, and they saw a sort of cause and effect of the capture by the Lower Congo of the drainage. Did you see any evidence for where the Congo came from in Angola?
I mean, in terms of the Congo, I mean, all of our evidence says it's an Oligocene event, yes, in terms of capture, and I think there's no
Definitely.
doubt on that. In terms of whether one switch is on, one switch is off, we didn't see clear evidence of that. Certainly there's tilting of the whole of that hinterland, and you sort of get and sort of a build-up of sediment into that southwest corner of the Glace Centrale. I think probably the whole of that story is more to do with mantly generated uplift and then headward erosion of those shorter headed rivers, rather than sort of one switching on, one switching off. I think that's more sort of a coincidence, if you like, on that.
Okay. Any other questions? I mean, Duncan, when you looked at the Nile, I mean, was it essentially climate or tectonics you felt that was causing the changes in sediment input there?
Well, both, obviously. I mean, again, it's a Oligocene river.
Yes, it is, isn't it?
Yeah, and it was, there's it's even more pronounced, so there's just nothing there apart from carbonates until you get to the base of the Oligocene. Whereas there were some form of precursors to the Ogooué in the Congo, albeit it seemed to have switched off in the Cretaceous. But once it got going, I think it was climate that controlled it.
I mean, the other thing you have for the Oligocene is a huge base level change.
Yeah, well, there's much more dramatic changes in climate in North Africa than there is in West Africa. Yeah.
There's a question here. Right.
Yeah. On Gabon, just wondering if drainage model can be used to predict the quantity of sediments in the pre-salt in North Gabon. I believe some explorers are planning to drill there, so I guess it's one of the key uncertainty as well.
Yes, I mean, the empirical models have huge error bars because they're purely based on present day observations, and that's a function of climate and the location and so on. So most of the models there will give you a sort of a ballpark figure, but I think there's more needs to be done. So yes, you can come up with a number. I think that there's more that can be done with some of the new landscape dynamic models that are being run, where you actually put in the tectonic uplift, you put in erosion into the model, and you actually do the calculations from process rather than simply empirical equations. So there are ways of sort of getting to those sort of numbers. I would say at the present time with the empirical models, huge error bars. It would probably help you a little bit, but I think you have to take those with some caution.
Thank you.
Any other questions for Paul?